studies, voltammetry, and amperometry. Sir, please.
Thank you, Shumaila. So, good morning to all of you. Once again, I welcome you. And today we are at the fourth day of this GYAN program on fascinating features of nano-dimensional smart materials. And I'm your course coordinator. I'll be taking you to the world of electrochemical studies, the voltammetry and amperometric technique, which are mainly used for and which I am going to talk of is energy storage devices and the sensor. The application of techniques like voltammetry and amperometry in energy storage and sensing. Before moving on to electrochemical technique, let me introduce you with Alessandro Volta. He's a scientist who developed the world's first battery in the year 1800 by placing sheets of zinc and copper electrodes by stacking them, and in between them he placed cloth immersed in an electrolyte. That cotton cloth immersed in an electrolyte basically serves as a medium for transfer of ions, and that assembly produces electric current for the very first time. And his surname Volta has become the unit of voltage, capital V, represented with capital V. There were few other scientists who have contributed greatly in the field of electrochemistry. One of the scientists was Michael Faraday. He worked in the area of electricity and electrochemistry and the chemical reactions and how electricity influence a chemical reaction. And you must be aware of the two very famous laws of electrolysis given by Faraday. He discovered the principle of electromagnetic induction. Now, what is electromagnetic induction? Earlier, it was believed that these two forces are different forces. The electric force is a different force, while a magnetic force is a different force. But later it was realized that they are not different forces, they are same forces, because whenever you have an electric current, it creates its magnetic field. And if you have a magnet, you take a coil, pass the magnet through that coil, it creates an electric current. So whenever we have magnetic field, it creates electric current, and vice versa is also correct. Do you have any idea about how many fundamental forces are there in the universe? Anyway, just to make this discussion more interactive, I think I should ask some minor questions. Even the online people can also answer. How many fundamental forces are there in nature? Any idea? Any guesses? Four of good. There are four fundamental forces of nature. Can you name those forces? Gravity is the right answer. Electromagnetic force, yes, the right answer. There are two more forces. These forces are running the universe actually. There are two more forces. One is called as the strong nuclear force and weak force. The strong force and the weak force. The strong force holds the protons having same charge inside the nuclei. It is so strong that even same charge particles having very high repulsion, they can stay together. They can stick together with the help of this force. And the weak force is because of which a nucleus emit alpha and beta particles to stabilize itself. That is the weak force. A strong force is among these all these forces, it is the strongest, but its influence, it influence only for a short distance only. While gravity, although it can be experienced even for long distances, even we are facing gravity on earth, and different planets, even black holes have very high gravity. So gravity, although can be experienced even at a long distances, but it is considered as weak force, because if it is very strong force, we won't be able to move, we won't be able to jump. So these are the four different forces. Earlier, the electric and magnetic forces have been considered differently, but now since they all have they have a vice versa effect, electric field creates magnetic field and magnetic field creates electric field, so they are considered same force. So Faraday explained how when electricity is passed through a solution, how the metals are being reduced and they are being deposited on the electrodes, and he has given two different laws. Then there was another scientist who is famous for wireless electricity transmission. His name is Nikola Tesla. He was working on the development of alternating current and electricity transmission. The coil developed by Tesla, it is still used in radio communication. It basically consists of two different coils kept at a distance. Both these coils have capacitors. One of the capacitor charges the coil, the current is generated, which creates a magnetic field, and and spark is created. With the help of that spark, electricity magnetic field is transferred to the other coil, and with the help of that magnetic field, an electric current is created in the other coil as well. So with the help of his invention, we can transfer that electricity with the help of magnetic effect to the other coil. So let us talk briefly about nanomaterials. Since this course is of uh, fascinating features of nano-dimensional materials, so all materials which have at least one dimension in the range 1 to 100 nanometers, they are called as nanomaterials, and they are used in medicine, electronics, biotechnology, energy, environment, and numerous fields. Do you have any idea about what are zero-dimensional materials? Even Professor Sapra was also telling, yes. Zero-dimensional materials means they do not have any, they cannot move freely in any dimensions. All they are trapped. Yes. No. So therefore, they are trapped inside. So like quantum dots or some other type of nanoparticles, which cannot move freely, they are called as zero-dimensional materials. You must be aware of all these. And then we have one-dimensional materials. So one-dimensional material are those which have one dimension. In one dimension, they can move freely. Examples are carbon nanotubes. Then we have nanowires, nanorods, etc. Then we have two-dimensional nanomaterials which can move in two different dimensions. Examples: graphene, magazines, and various other metallic nanoparticles like molybdenum sulfide, disulfide. Why is this not working? And then we have three-dimensional nanoparticles which can move in all three dimensions, like the bulk material. But those bulk material have characteristics of nanoparticles, like they have either the pore size of nano range, they are like nanocomposites, aerogels, dendrimers, etc. Now, as you all know that because of very high surface area, as we keep on reducing the size of a material, the surface area increases, the surface to volume ratio increases, and most of the properties, most of the application of a material are basically based on their surface, because when we are doing a reaction, it is the surface which is involved. So if higher the surface area, more fluorescences will be there. We the properties shown are even more pronounced because of their very high surface area. So these nanoparticles have high conductivity, large surface to volume ratio. They are also used for surface plasmon resonance and like in electronics and optical applications. And they have very good electrocatalytic properties or in electrochemical properties as well. And therefore, because of those properties only, they are used in energy storage and sensing applications. Now, let us move on to electrochemical methods. Electrochemical methods are those methods which involves the principles of electrochemistry. And electrochemistry principles, as I told you, I think yesterday also, that the electrochemical reactions are those reactions in which the electrons are being transferred from a material to the electrode and from electrode to the material. Means the electrodes and electrolytic and an external circuit is involved in these reactions. One of the substrate undergo oxidation, the other undergoes reduction, and in this way the electrons that flows from one side to other, it creates an electric field or an electric current. The two main applications or the two main methods that comes under the category of electrochemical methods are voltammetry and amperometry, that I am going to discuss in detail. So what is voltammetry? Can anybody tell me what is voltammetry? I told you on day one as well. Any idea about voltammetry? In voltammetry, we give a variable potential to a system and then we measure the corresponding current. So we are giving variable potentials. So potential is also variable, which is an input, while the output is current and the graph is I versus V. Current versus potential graph is the output of an voltammetric system, voltammetric studies. On the other hand, in case of amperometry, what do is we keep the potential fixed, and at that fixed potential, we measure the current of a system with respect to time. So the output graph of an amperometric system is I versus T at a constant, at a fixed voltage. This is the classification of electrochemical methods. Broadly, they are divided into two categories, the static techniques and the dynamic techniques. In case of static techniques, we have potentiometry. Potentiometry refers to the measurement of potential, but not the voltage actually. Most of the time, we synonymously use the word electromotive force and voltage. Do you think they are really same? No, not at all. Electromotive force is the voltage of the system when no current is being drawn from the system. The moment we draw current from the system, now the difference between its electrode's potential is called as the potential difference or the voltage. It is not the electromotive force. So electromotive force, which is also called as open cell voltage or open cell potential, can only be obtained by an indirect method which is called as potentiometry. So potentiometry is a method for measuring the open cell potential or the electromotive force of the system by introducing a standard Wesson cell. I think you might have heard the name of standard cell whose potential remains constant irrespective of the temperature. Means the cell potential does not depend upon the temperature. So that standard cell is used to calculate, to determine the potential of a cell or a system without drawing any current. So if we, for example, if I give you a cell and I ask you to measure the electromotive force, you have a voltmeter, you connect the voltmeter, tell me the voltage. Sir, this is the voltage reading in the voltmeter. So this is the open cell potential or the electromotive force. No, that is the potential difference between the two electrodes. That is not the electromotive force, because when you connected the voltmeter draws current from the cell. So the value goes down. It is not the actual electromotive force. Electromotive force or the open cell potential can be measured by an indirect method by using a standard Western cell and making a circuit, which I think I should explain some other time, and some of the student I think I have explained in class that it is an indirect method. So potentiometry is for measuring the potential without drawing the current. Now in the dynamic techniques of electrochemical uh, methods, we have two options. We have two classes. Either we can control the potential or we can control the current. If we control the potential, again, we have two options. We can either fix the potential at a particular value or we can vary the potential. If the potential is fixed, you can see here, in case of control potential, if the potential is fixed, what do we get? Amperometry. While if the potential is variable, is variable, not valuable, it is variable, then there are again two conditions. If we are stirring the solution, yesterday I told you that if we are stirring the solution, we are mixing the solution, so we are giving rise to a new mode of mass transfer which is called as convection. There are three modes of mass transfer I told you yesterday. First is the diffusion, second is the convection, and third is the migration. When we apply potential to an electrode, opposite charge, the charged particles move to the opposite electrode. That is called as migration. So there are two possibilities when we are changing the potential. Either the solution is stirred. If the solution is stirred, the two voltammetric studies are called as hydrodynamic voltammetry or stripping voltammetry. On the other hand, if the conditions are quiescent, we are not stirring it, there are few other techniques, linear potential, then we have another type of stirring voltammetry technique, then pulse voltammetry and cyclic voltammetry techniques. In cyclic voltammetry also, we do not stir the solution. We do not mix the solution, which means that in case of cyclic voltammetry also, there is no convection mode of mass transfer. These three mass transfer modes are very important for electrochemical studies. So this is the basic classification of electrochemical methods. Now before starting the voltammetry or amperometry technique, I should first explain you the difference between resistance and impedance. Resistance basically generates from a resistive circuit only. While if we have capacitive circuit or a circuit containing capacitor as well as inductor as well as resistance, then the sum of all these obstructions will be the impedance of the circuit. So impedance means you are already covering the resistance and you are also using some other types of obstructions in the flow of current. That obstructions comes under the category of reactance. So impedance means resistance plus reactance. The reactance is not significant in a direct DC circuit, but in case of AC circuit, the reactance is very significant and you have to consider it. So while considering the total resistance, we use the word impedance for an AC circuit. Clear? So both the terms, resistance as well as impedance, they are basically obstruction in the flow of current. That's it. And since they are obstructions, the unit is also same ohm. While resistance is mainly studied in DC circuits, we study impedance in case of alternating current circuits, where the current is changing its positions. Resistance is mainly pure, it is a pure quantity. It is only a real quantity, while impedance involves real as well as imaginary part. Impedance, as I told you earlier, that it is even a more comprehensive term. If you are considering impedance, you are considering all sorts of obstructions, all types of hindrances in the flow of current. So reactance basically, resistance basically is the dissipation of energy, while reactance involves the storage as well as release of energy. So it is, if you are talking of impedance, that means you are considering energy dissipation, energy storage, energy release, all sorts of resistances. This is, this way you can see that the impedance becomes very high because it involves, along with the resistance, you have reactance as well. And the impedance is calculated with by just like a Pythagoras relationship. The impedance square, Z square, it is denoted by Z, is equal to the R square plus X square. R is the resistance and X is the reactance of the circuit. Again, since it is a Pythagoras relationship, so again the unit will be same, the ohm. Now depending upon whether we have more of a reactive circuit or more of a resistive circuit. For example, if in a circuit we have more resistive load, then we can say that it is more of a resistance circuit. While on the other hand, if a circuit has more of a reactive load or an inductive load or a capacitive load, we can say that it is more of a impedance type. If either of the component value is large, is a larger magnitude than the other, जो भी ज़्यादा होगा, if resistive load is high, we can call it that it is a type of resistive circuit. Otherwise, if it is a type of a reactive circuit, it considers both these parameters. Now, as you all know that in case of voltammetry, we have two techniques. We have many techniques, but these are the two common, LSV and cyclic voltammetry. So voltammetry refers to the measurement of current produced in a system against a variable applied voltage. And it is of two types. On the other hand, amperometry refers to the measurement of current against a fixed voltage. These are the duck-shaped curve for ideal systems. So voltammetry is basically a time-dependent potential excitation signal is given to the, of course, to the working electrode, because the working electrode is the main electrode where the analyte is either oxidizing or reducing. So we are mainly concerned with the analyte. Analyte is called as the compound of interest. So working electrode is mainly responsible for the oxidation or reduction of the compound of interest. So a time dependent means we have to first of all select the range, as we have shown you yesterday. We have to select the range, that what range of potential we are going to cover it, and at what scan rate. For example, if it is changing from 0 to plus 1 volt, then at what rate is it changing? For every second, either it will go up by 100 millivolts, or maybe by 50 millivolts, or even by 5 millivolts. We have to select that scan rate also. Sorry. Now, when the voltammetric techniques was discovered, was developed for the first time, the very first technique of voltammetry that was developed, it was developed by Jaroslav Heroski in the year 1920, and that technique is called as polarography. So, polarography is also a sort of a voltammetric technique, but in case of polarography, we use mercury electrodes as a working electrode. He got Nobel Prize also in 1959. We use mercury electrode in polarography, and there are three types of mercury electrode possible. These are the three electrodes. The first is called as the hanging mercury drop electrode, HMDE. In this electrode, we have a capillary tube, we have a mercury filled over here, and there is a screw. We rotate the screw, it pushes the mercury forward. The mercury will form a drop. When we push, when we rotate the screw more, it will pushes the mercury, the drop becomes heavy and it falls due to gravity. Therefore, it is called as hanging mercury drop electrode. As long as the size of the drop remains small, it is stay hanging. When the size becomes big, it falls off the electrode. Then we have a dropping mercury electrode. In case of dropping mercury electrode, we are not using the term hanging because it is an open system. We have a reservoir of mercury, liquid mercury, and it is connected to a capillary. It moves down, the drops comes out, the size of the drop increases, and a moment will come when it becomes heavy enough to fall of this electrode. When it falls, when it fell down, it is immediately replaced with a new drop. It is like a one electrode is being replaced with a new one. Then we have a static mercury drop electrode. In case of static mercury drop electrode, we use solenoid valves. Solenoid valves are basically time dependent valve. You can set the timer, you can close the valve at a particular time that you have predetermined. The valve will open, required amount of mercury is allowed to pass to form the drop and fall off. So it is called as static because here it is static unless and until the valve opens and the mercury is moves down. So these are the three types of electrodes which are used, and while using this polarography, the very famous equation which is used to calculate the diffusion current is called as Ilkovich equation. ID is the diffusion current and it is equal to 607 NCM to the power 2 by 3 T to the power 1 by 6 under root D. ID is the diffusion current in microamperes. 607 is a constant value that is basically dependent on various factors, including the Faraday constant, the density of Hg, the conditions of those experiment, temperature, etc. N is the number of electrons involved in the electrode reaction. D is the diffusion coefficient in centimeter square per second. How fast the material is diffusing, the ions are diffusing from one place, from bulk of the solution towards the electrode. गिलास होगा यहाँ पे? गिलास होगा? थोड़ा सा बताना था मुझे, शीशे का गिलास मिल जाता तो बता सकते हैं. M is the mass of Hg flowing through the capillary, milligrams per second. T is the time in seconds, and C is the concentration. So with this, you can calculate the diffusion current using the mercury electrode. Now, why do we prefer Hg electrode? Why do we prefer mercury electrode in polarography? Because one of the advantage of mercury electrode is that it can be easily mixed with any metal to form an amalgam. For zinc, copper, other electrodes, it is not possible to mix them very easily. But with mercury, you can mix them, you can form an amalgam very easily. The other thing is that there is a term called as overpotential. Overpotential is basically the difference in the potential between the theoretical value of a certain reaction. For example, there is a reaction. For that reaction, the theoretical value of potential is, for example, 1 volt. But practically, you have to give 1.5 volt to carry out that reaction. So the difference between these two, 1.5 and 1, the zero point 0.5 volt, it is basically the overpotential. Like Professor Sapra has said yesterday that hydrogen is evolved by the reduction of H ion at 0 volt. But if we have zinc electrode there, the same reaction will occur at 0.76 volt. So that is the overpotential for zinc electrode. So if we are using zinc electrode, the H ions, because it's for it, the zinc electrode, it is minus 0.76, which can be very easily achieved. If you are doing a reaction with zinc or a copper electrode, it will immediately forms hydrogen gas. But if you are using mercury electrode, for mercury the potential is plus 0.07, plus 0.70 volts, which is in plus direction. Plus or minus is only the direction. Minus means it is, the voltage can never be in minus. Minus means the voltage is lesser than a reference value. For example, 0.7 minus 0.7 means there is a reference value and the potential is 0.7 volts lesser than that reference value. On the other hand, if you have plus 1 volt, that means from a reference value, it is plus 1 volt. Clear? So for mercury electrode, the overpotential is plus 0.70 and therefore it is difficult. While in case of zinc, it is minus 0.76, which can be very easily achieved, and hydrogen is start evolving during the process. Therefore, we avoid those electrodes and we prefer hydrogen because it has a high overpotential for this particular reaction. And overpotential is basically, write down the difference between the theoretical and the experimental voltage for a particular reaction. So this is the first reason that it has a high over potential, so it prevents release or evolution of hydrogen gas. The second reason, it forms amalgam. And third reason, the mercury, because of its liquid nature, it renew itself every time. As I told you, in case of hanging mercury, you move the screw, drop becomes bigger, falls off. In case of dropping mercury, there is no control, it will continuously, drops will fall off and new drops will come. In case of static electrode, although it is static, but if you have fixed the timer, the timer, the time, and once the time is, once the timer opens, the mercury drops falls off, replaced with a new drop. So it renews itself. Therefore, it is preferred. Again, the 2 and 3 electrode systems. I think you are already aware of these two systems. Earlier we use 2 electrode system. We have working electrode and counter electrode now. But if you are using two electrodes, it is called as the full electrode system or the full cell system, and it will give you the potential difference between the two electrodes, main electrodes. But if you want to study the behavior of working electrode only, then you have to place a third electrode. And then with respect to that third electrode, you can study the potential or the electrochemical behavior of your working electrode. Therefore, we now prefer to use a three electrode system in which we have a working electrode, we have a reference electrode, and we have a counter electrode. We connect reference and counter to one terminal and working to the other terminal. Already discussed. Now Faradayic and non-Faradayic currents. I told you yesterday. Can anybody tell me what are Faradayic current? What is a Faradayic current and what is a non-Faradayic current? Or what is a Faradayic process? The Faradayic process produces Faradayic current, and non-Faradayic process produces non-Faradayic current. So what is a Faradayic process? Redox reaction. For example, you have an analyte. The analyte is oxidizing, releasing electrons. Those electrons are taken up by the electrode. Now they are circulating through the external circuit. The current generated in this way is called as a Faradayic current because it is obtained by a Faradayic process. It is obtained by an electrochemical reaction where the analyte undergoes oxidation. Clear? On the other hand, if current is generated by a non-Faradayic process. Now, what is a non-Faradayic process? Suppose you have a system, you have two electrodes and some electrolyte in it. Now you have changed the potential of one of the electrodes suddenly, making it a little bit more positive. आपने out of the two electrodes in the system, एक electrode का you have given some potential by some external source. एक बैटरी लगा के आपने potential दिया और उस electrode का potential, that electrode acquires a positive charge. The moment it acquires positive charge, now in solution we have, the solution is neutral, we have anions as well as cations. Since the electrode now suddenly after giving the potential, it has acquired a positive charge, all positive ions, all cations start moving from away from each other, from this particular electrode, while all the negative ions which are present into the solution, they start moving towards this electrode, and because of this movement of ions, current is being generated. But here no redox reaction is taking place, none of the ion is oxidizing or reducing. Therefore it is a non-Faradayic phenomena, and the current generated by this phenomena is called as a non-Faradayic current. Clear? It is not following the Faraday's law, while the former it was following the Faraday's law. The current which is generated by this sort of non-Faradayic process is called as a, although it is a non-Faradayic current, but it is also called as a charging current. Why? Because this current, this transient current is generated just after giving a charge to a particular electrode. As I just mentioned that if you have given sudden charge, a positive charge, so positive charge moves away, negative charge moves towards that electrode, the current is generated. So if, since this current is being generated by giving charge to an electrode suddenly, therefore it is also called as charging current. So charging current is a type of non-Faradayic current. There is one more term, because I think I should, before starting voltammetry and amperometry, I should explain the basic term so that you may not get confused. There is another term called as residual current. Can anybody tell me any idea about residual current? Those who are sitting at the top? Anyway, the residual current also has two components, the Faradayic component as well as a non-Faradayic component. But the current, the Faradayic component of residual current is not because of analyte, because if it is because of analyte, it is not called as the residual current. Residual current means that it is not generated because of the redox reaction of analyte, it is not generated because of oxidation or reduction of analyte. It is not generated because a Faradaic process of analyte. It is generated by the Faradaic process of impurities which are present in your system. That's it. And the non-Faradaic component, again, it is because when you give the charging to an electrode, ions moves, current is generated. So residual current is basically the current which is due to the oxidation or reduction of the impurities, as well as if you have given some charge to the electrode due to non-Faradaic process. This is called as residual current. And the point to be noted here is that if a Faradaic current is generated due to reduction of the analyte. For example, you have an analyte over there, current is coming from the electrode, the electrons are released and that analyte accepted those electrons and undergo reduction. The Faradaic current generated due to the reduction of an analyte is called as cathodic current, and its direction, its sign is positive. Write down. This is very important point. Most of the students confused. While the Faraday current due to the oxidation of analyte is called as anodic current and its sign is negative. Write down. Faraday current, analyte reduction called as cathodic current, plus sign. Faraday current due to analyte oxidation is called as anodic current, its sign is negative. Water bottle. Yeah. Now let us take the example of ferricyanide. You have, for example, ferric ion in solution, Fe plus 3, and you are reducing them to ferrocyan, Fe plus 3 to Fe plus 2 at the working electrode. Suppose initially, since the reaction has not started, you have only Fe plus 3 ion because this reaction is not started yet. For this reaction, the required potential is plus 0.356 volts. Now, when we start the reaction from a positive value, for example, we have given initially plus 1 volt or even plus 0.5 volt, nothing will happen. But as the potential goes down and it reaches to a value plus 0.56 volts, immediately Fe plus 3 start reducing to Fe plus 2. Now, for example, you have a system and you have a working electrode over there, and you have placed some ferric ions into it. Now no ferrous ions are present. You give the potential. Initially the potential value was plus 0.56. Nothing will happen. But as the potential drops and it reaches to plus 0.356, at that particular potential, the ions which are present in the vicinity or which are present at the working electrode, they immediately undergo reduction from Fe plus 3 to Fe plus 2. Now the concentration of Fe plus 3 at the working electrode goes down because all Fe plus 3 has been converted to Fe plus 2, while there are many Fe plus 3 ion in the bulk of the solution. So there will be a concentration difference of Fe plus 3 ion near the electrode, all Fe plus 2 because Fe plus 3 has been reduced to Fe plus 2. On the other hand, we have plenty of Fe plus 3 ion in the bulk of solution. They start moving due to diffusion. This is called as diffusion, the mode of mass transfer. They start moving towards the working electrode. The moment they reach working electrode, they receive sufficient potential and they immediately undergo reduction to form Fe plus 2. This is the reduction reaction where only diffusion is occurring as a mode of mass transfer. Clear? Now a point will come when the concentration of Fe plus 2, since it is going up because of the reduction, while Fe plus, earlier we have 0 Fe plus 2 and we have very high Fe plus 3 because all the ions were of Fe plus 3. As the reaction proceeds, Fe plus 3 goes down because it is reducing into Fe plus 2, while Fe plus 2 goes up. Now a point will come when the concentration becomes equal. Now the diffusion of the ions will stop. No, the current will no longer exist. Current will only exist when there is a concentration difference. Clear? So this sort of movement of ions is called as diffusion. You have to do nothing for diffusion. You don't have to apply any charge. You don't have to mix the solution. It will move on its own just because of the concentration difference. So for example, this is the system. खाली bottle है, एक glass दे दो, pen दो. For example, if this is the system, you have an electrode, working electrode over there. On the other side, we have a reference electrode. Now we put some Fe plus 3 ions into it. So the concentration of Fe plus 2 at this time is 0. The potential is 0. We have not started the reaction. Now when we start the reaction, we give the potential. Initially the potential value was high. Nothing will happen. As the potential drops down, it reaches to plus 0.356. Immediately the ions which are present at this electrode, or it is near this electrode, they immediately undergo reduction. The moment they undergo reduction, there are two boundaries. One is called as the surface of electrode, the other is called as the bulk of solution. So ion present at the surface of the electrode, they undergo reduction to form a ferrous ion, while the rest of the solution still contains many Fe plus 3 ions. So when the concentration of Fe plus 3 goes down here, while the rest of the solution has, they start moving. They start moving towards the electrode. As soon as they reach to the electrode, they undergo reduction. So the Fe plus 2 keeps on increasing, while Fe plus 3 keeps on decreasing. And the moment when the concentration becomes equal, migration, the diffusion of ions will stop, the current will stop. Again, I just want to explain you the mode of mass transfer. Diffusion we have just covered. It occurs when the concentration of ions or molecule is different at the surface from the bulk of the solution. If we apply potential to completely reduce, जैसे मैंने अभी कहा, more Fe3 will diffuse. जैसे जैसे as soon as the Fe ion near the electrode undergo reduction, more Fe ions will come. जितना ज़्यादा यहाँ से reduce होगा उतना ज़्यादा आएगा. कब तक आता रहेगा? Unless and until the concentration of Fe plus 3 and Fe plus 2 becomes equal. The second type of mass transfer is convection. It is only possible if we are stirring the solution. The result will be different. If diffusion is taking place, the graph will be different. If convection is also taking place, the graph will be different. I'll show you the graph. So from the graph only you will observe, when you do it for your test system, in your research or in master's or undergrad project, just by looking at the graph, you will observe that whether convection is taking place in your system or not, whether migration or diffusion is taking place or not, or whether all the these most mode of mass transfers are taking place. Just like I explained you in case of GCD, that if you are doing GCD, you will first of all identify by looking the graph whether they are EDLC, or if the curves are there, you get to know that they are pseudo capacitive. And from these curve you will identify specific capacitance, then energy density, then power density, and various other parameters. You will also get to know about the cycling stability. You will also get to know about the performance of your cell after 1000 cycles. So from one curve you got many data. Similarly, from the curve you can easily identify about the mode of mass transfers. Then third is the migration. Migration is only possible when you have charges on two electrodes. One is positively charged, one has plus Q charge, for example, the other has minus Q charge, and the ions will move towards the opposite electrode. This sort of movement, or this sort of transfer of ions under the influence of charge is called as migration. The diffusion current for such system, other than polarography, the diffusion current for such system is given by ID is equal to NFAD C bulk minus C x0 upon delta. C bulk means the concentration of analyte. For example, in this particular case, our analyte is Fe plus 3. So the concentration of analyte in the bulk, while the concentration of analyte x0 means at the electrode, at zero distance from the electrode, means at the electrode surface. So the concentration of Fe plus 3 at electrode surface is represented by Cx is equal to 0, while the concentration of Fe plus 3 in the whole of this solution is called as C bulk. N is the number of electrons. Again, F is the Faraday's constant. A is the area of electrode. D is the diffusion coefficient. While delta is the, can anybody tell me, where is Aditi? Delta is the thickness of diffusion layer. The thickness of the diffusion layer increases as the reaction proceeds. जब जितना diffusion layer thickness means जहां तक diffusion operate हो रहा है, जहां तक diffusion, the distance up to which diffusion is occurring. For example, initially ions are here while the rest of the Fe plus 3 ions are far away. If we are not doing anything, Fe plus 3 will reduce to Fe plus 2. तो सबसे पहले जो the ions which are closer to the electrode, first of all they will come. Then the ions which are farther from electrode, then they will come. And at the last, ions which are at the farthest place from this electrode will also move. So this shows that initially diffusion was taking place to a was occurring at very short distance. Then the distance of diffusion or the limit of diffusion increases. Then after some times it even increases further. So this shows that diffusion increases with time if no other mode of mass transfer is occurring. If diffusion is the only, write down, if diffusion is the only mode of mass transfer occurring in a system, then the thickness of diffusion layer or the limit of diffusion that increases, that limit increases. बड़ा कंटेनर होगा उसके भी दूर से भी आयन आना शुरू हो जाएंगे, ठीक है, as the reaction proceeds. जी, diffusion layer की thickness delta you can identify with the help of these data from the diffusion current, because diffusion layer is in, if the length of the, or the thickness of diffusion layer is high, then that means diffusion is influencing for at a large, even at a long distance. That means more ions are coming, that means more current will be generated. So this thickness of the layer is proportional to the current, or the current is proportional to the thickness. So with the help of current, if the current ID value is high, that means the thickness of the layer or the delta we can relate it with. Clear? So we can, with the help of current and these parameters, we can calculate the thickness of the diffusion layer delta. So F is the Faraday's constant, A is the area, D is the diffusion coefficient, again C bulk and C x is equal to 0 is the concentration at electrode surface and bulk of the solution, and delta is the thickness of the diffusion layer. The thickness increases as the reaction proceeds. Higher the thickness, lower will be the current, lower the thickness, because they are inversely proportional. You can see in this figure that earlier we have FeCN 6 3 negative, here Fe is in +3 state. It is coming towards electrode, and the moment it comes near the electrode, an electron is being given by the electrode. Fe plus 3 accept this electron, immediately form Fe plus 2, and then moves away. In this way, this is type of a shuttling service. From here we are getting +3, taking electron, undergo reduction, and the moment it forms Fe plus 2, it moves away from the system. This way diffusion operates. Now, this mode of mass transfer has a strong influence on the shapes of voltammograms. As I said just now, that from the shape of the curve which you obtained, you can identify what kind of mass transfer processes are taking place or not, because they have a strong influence. The two common shapes of voltammograms are like this. Even such shapes are possible in CV as well as LSV. It is only a part of the curve I have shown here. Even in CV also, we may get such type of peaks and then a cyclic curve. And even in LSV also, where we have only a line, in that line also we can have this sort of curve. So the shapes of voltammograms depends upon how we measure the current and how the mass transfer is taking place. Suppose convection is also taking place. Convection is occurring as well as diffusion is occurring, both in this particular system. If I say convection is occurring, that means I am stirring this solution. मैं इसको स्टीयरिंग कर रहा हूँ एंड बिकॉज ऑफ स्टीयरिंग अब सोचिए थोड़ी देर के लिए कन्वेक्शन की बात सोचिए. If I am stirring the solution also, what will happen? The ions which are present near the electrode, Fe plus 3 ions, they will reduce to form Fe plus 2. The moment they form Fe plus 2, the concentration of Fe plus 3 is low here, this side, while all this portion has high concentration. But since we are stirring it, it will immediately stir the solution and make the concentration constant, uniform in the whole of the solution. जब ऐसा होगा then there will be no ऐसी कोई सिचुएशन नहीं आएगी कि एक वक्त में बहुत ज़्यादा that a number of ions undergo reduction at a particular time and we got a peak, because all the time because of this stirring the concentration remains uniform. Therefore instead of a peak we got this sort of curve. This type of current is, this is called as limiting current. Limiting current IL is only possible when convection is taking place. Write down. Limiting current is possible when convection is taking place, when we are stirring the solution. Because when we are stirring the solution, the concentration remains uniform. And since the concentration remains uniform, there will be no peak like this one. The curves are smooth. Even the current is increasing, it is still quite smooth because the concentration is uniform. जब concentration घट रही होगी तब भी वो यूनिफॉर्म रहेगी. फॉर एग्जांपल इनिशियली इट इज 1 मोलर concentration of Fe plus 3 ion. Now since some of the Fe plus 3 ions have been reduced to Fe plus 2, now the concentration becomes 0.8. So the whole solution becomes 0.8. It is not that कि यहाँ this point has 0.9 while this point has 0.8 while the middle portion has 0.7 and this portion which is very close to the electrode it is having 0.4. This will occur only when diffusion is taking place, but since convection is also taking place we are stirring the solution, then all the times the concentration remains uniform. If it is going down, the whole concentration still remains same, 0.8 in the whole solution, then again 0.7, 0.6 and 0.5. It will go down in this fashion, and therefore we do not get any sharp peaks. Even when the current increases, the curve is smooth. This type of curve is, this current is called as limiting current, and it is only possible when convection is also taking place. On the other hand, if convection is absent, if there is no convection, then what will happen? Initially, no current because the system is not started. The moment we start giving potential, some of the ions are getting converted into Fe plus 2. After a certain period of, so the current will go in increasing, and a point will come when the concentration near the electrode is going down and there are no more ions left in the bulk of the solution even to fill it up, fill this gap. So the concentration, the current will go down. This type of current is called as peak current. This is called as limiting current IL. This is called as peak current IP. If you are getting an IP in your curves, this means diffusion is taking place. If you are not getting any sharp peak, you are getting smooth curves. This shows that convection and diffusion both are taking place. Now, how will you determine the concentration of analyte at a particular point? Let us assume the same redox reaction where we have ferric cyanide in which we have Fe plus 3 ions, and now they are reducing to Fe plus 2 ions. Suppose we are stirring the solution also. Let us assume that only Fe3 is present in the bulk of solution and that we are stirring the solution. It is, I am talking out before the start of the reaction, we have Fe plus 3 only and we are stirring the solution. Now when we apply potential, again there will be a reduction of Fe plus 3 to Fe plus 2. The moment it happens, more Fe plus 3 ions are moving for reduction. Again, since we are stirring the solution, the concentration remains same. The current in this case can be given by K naught the concentration of Fe plus 3 in bulk minus the concentration of Fe plus 3 at x naught. Clear? Ko is equal to NFAD upon delta, because this is the equation. ID is equal to NFAD C bulk minus C x naught upon delta. So we have replaced NFAD upon delta, because they all are constant terms. We have replaced NFAD upon delta with K naught, while we keep these two terms because they are now the main terms which we are going to determine. So we have replaced FAD NFAD upon delta with K naught. K naught is NFAD upon delta. It is written over there, and these two other terms which we are focusing now. When we reach the limiting current value, because since we are, as I said, we are stirring the solution, it is convection taking place. So the curve will be like this one. Now limiting, when we reach the limiting current, means this is the maximum current. Now not, it is not possible to have more current. At this particular point, the concentration of Fe plus 3 and Fe plus 2 are same. So when we are reaching
So
limiting
when we
current,
are
this
reaching
means
limiting current,
all
this
the
means
Fe plus
all
3
the
ion
Fe
which is
plus
present
3
near the
ion which
electrode
is
is
present near
being
the electrode
oxidized.
is being oxidized.
क्योंकि अगर बचा होता
क्योंकि अगर बचा
is
होता
being
is
reduced,
being reduced,
because
because
if it is
if it
still
is still
left,
left,
it would
it would
undergo
undergo
reduction.
reduction.
Current
Current
will
will
again,
again,
current
current
should
should
have
have
some
some
value,
value,
but
but
since
since
it
it
is
is
already
already
limiting
limiting
current,
current,
no,
no,
the
the
current
current
is
is
not
not
going
going
up.
up.
This
This
shows
shows
that
that
all
all
the
the
Fe
Fe
plus
plus
3
3
ion
ion
which
which
is
is
present near
present
the
near the
electrode
electrode
has
has
already
already
been
been
reduced
reduced
to
to
Fe
Fe
plus
plus
2.
2.
So
So
the
the
concentration
concentration
of
of
Fe
Fe
plus
plus
3
3
at
at
electrode
electrode
surface
surface
is
is
0.
0.
Therefore,
Therefore,
Fe
Fe
plus
plus
3 is
3 is
0
0
at
at
x
x
is
is
equal
equal
to
to
0
0
means
means
the
the
electrode
electrode
surface.
surface.
Now,
Now,
when
when
we
we
put
put
x,
x,
this
this
Fe
Fe
plus
plus
3
3
x
x
naught
naught
0,
0,
the
the
equation
equation
becomes
becomes
ID
ID
is
is
equal
equal
to
to
K
K
naught
naught
Fe
Fe
plus
plus
3
3
bulk.
bulk only.
So,
So,
from
from
this,
this,
we
we
can
can
easily
easily
calculate,
calculate
if
if
we
we
know
know
the
the
value
value
of
of
IL,
IL,
K
K
naught,
naught,
the
the
value
value
of
of
constant
constant
is
is
already
already
known.
known.
You
You
can
can
easily
easily
calculate the
calculate the
concentration of
concentration of
analyte at
analyte at
any
any
point.
point.
Clear?
Clear?
So
So
this
this
is
is
what
what
we
we
were
were
discussing
discussing
in
in
determining
determining
concentration.
concentration.
First of
First
all,
of
if
all, if
convection
convection
is
is
taking
taking
place,
place,
I
I
naught
naught
is
is
equal
equal
to
to
K
K
naught.
naught.
If
If
you
you
do
do
not
not
want to
want to
put
put
K,
K,
you
you
can
can
put
put
directly
directly
NFAD
NFAD
upon
upon
delta,
delta,
Fe
Fe
plus
plus
3
3
bulk
bulk
minus
minus
Fe
Fe
plus
plus
3
3
x
x
naught.
naught.
And
And
since
since
we
we
have
have
reached
reached
the
the
limiting
limiting
current,
current,
that
that
means
means
no
no
more
more
current
current
is
is
going
going
being
being
generated.
generated.
Now
Now
all
all
the
the
Fe
Fe
plus
plus
3
3
ion
ion
which
which
are
are
present
present
at
at
the
the
electrode
electrode
has
has
already
already
been
been
converted
converted
to
to
Fe
Fe
plus
plus
2.
2.
So
So
the
the
concentration
concentration
of
of
Fe
Fe
plus
plus
3
3
at
at
the
the
electrode
electrode
surface
surface
means
means
Fe
Fe
plus
plus
3
3
x
x
is
is
equal
equal
to
to
0.
0,
It is
is
already
already
0.
0.
We
We
just
just
put
put
it
it
0.
0.
The
The
concentration,
concentration,
the
the
equation
equation
becomes
becomes
I
I
is
is
equal
equal
to
to
K
K
naught
naught
Fe
Fe
plus
plus
3
3
bulk
bulk
means
means
the
the
concentration
concentration
of
of
ferric
ferric
ion
ion
in
in
the
the
bulk
bulk
of
of
the
the
solution
solution
in
in
the
the
whole
whole
of
of
the
the
solution.
solution.
And
And
from
from
the
the
value of
value of
current
current
and
and
putting
putting
these
these
constant,
constant,
you
you
can
can
easily
easily
determine
determine
the
the
concentration of
concentration of
analyte
analyte
at
at
that
that
particular
particular
time.
time.
Determining
Determining
the
the
standard
standard
state
state
potential.
potential.
Again,
Again,
consider
consider
the
the
same
same
equation.
equation.
The
The
reduction
reduction
of
of
iron
iron
plus
plus
3
3
from
from
plus
plus
3
3
state
state
to
to
plus
plus
2.
2.
And
And
again
again,
consider
consider
that
that
we
we
are
are
stirring
stirring
the
the
solution.
solution.
That
That
means
means
that
that
convection
convection
is
is
taking
taking
place.
place.
So
So
according to
according
the
to the
Nernst
Nernst
equation,
equation,
E
E
cell
cell
is
is
equal
equal
to
to
E0
E0
cell,
cell,
the
the
standard
standard
state.
state.
So
So
E0,
E0,
the
the
standard
standard
state,
state,
and
and
the
the
condition
condition
of
of
Fe
E
plus
plus
3 is
3 is
getting
getting
reduced
reduced
to
to
Fe
Fe
plus
plus
2
2
minus
minus
0.059.
0.059.
कहाँ
कहाँ
से
से
आता
आता
है
है
2.303
2.303
RT
RT
upon
upon
NF.
NF.
When we
When we
put
put
RT
RT
and the
and the
value
value
of
of
F
F
and
and
multiply
multiply
with
with
2.303,
2.303,
it
it
changes
changes
itself
itself
into
into
0.059.
0.059,
0.059 divided
divided
by
by
n,
n,
n
and
is
is
the
the
number
number
of
of
electrons.
electrons.
So
So
here
here
in
in
this
this
case
case
also
also
we
we
have
have
one
one
electron
electron
only,
only,
so
so
even
n
n can
can
be
be
replaced.
replaced.
And
And
then
then
we
we
have
have
log
log
products
products
upon
upon
reactants
reactants
concentration. So
concentration.
Fe
So
plus
Fe
2
plus 2
upon Fe
upon Fe
plus
plus
3.
3.
Okay,
Okay,
whenever
whenever
we
we
are
are
talking
talking
of
of
electrochemical
electrochemical
reaction,
reaction,
we
we
always
always
do
do
at
at
the
the
electrode
electrode
surface.
surface. Because the portion of the solution which is far off the electrode surface, nothing is happening over there except the diffusion of ions. The reduction or oxidation is only taking place at the electrode surface. रिडक्शन ऑक्सीडेशन जो भी होगा वो इलेक्ट्रोड सरफेस पे होगा. तो हम जब भी इलेक्ट्रोकेमिस्ट्री की बात करेंगे, इलेक्ट्रोकेमिकल रिएक्शन की बात करेंगे, वी ऑलवेज टॉक ऑफ द इलेक्ट्रोड सरफेस. बल्क ऑफ सॉल्यूशन में कुछ भी नहीं हो रहा, सिर्फ इतना हो रहा दैट आयंस आर मूविंग, जैसे जैसे यहाँ कॉन्सेंट्रेशन कम हो रही है दूसरी तरफ से आयंस उसकी तरफ आ रहे हैं। जो इलेक्ट्रोकेमिकल पार्ट है, जो रिडक्शन ऑक्सीडेशन पार्ट है, वो सिर्फ यहाँ पर हो रहा है।
क्लियर?
क्लियर?
So we
So we
can
can
develop
develop
this
this
relation in
relation
the
in the
form
form
of
of
current
current
as
as
well.
well.
Since
Since
limiting
limiting
current
current
अभी हम
अभी हम
लोगों ने
लोगों ने
कैलकुलेट
कैलकुलेट
किया है,
किया है,
पिछली
पिछली
इक्वेशन में
इक्वेशन में
लिमिटिंग
लिमिटिंग
करंट
करंट
के
के
नॉट
नॉट
Fe
Fe
प्लस
प्लस
3
थ्री
बल्क
बल्क
ऑफ
ऑफ
द
द
सोल्यूशन।
सोल्यूशन।
ये
ये
जो
जो
इक्वेशन
इक्वेशन
था,
था,
अभी
अभी
यहाँ
यहाँ
से
से
Fe
Fe
प्लस
प्लस
3
थ्री
एक्स नॉट इज
एक्स नॉट,
मतलब x इज इक्वल टू 0 निकालेंगे तो आई एल माइनस आई अपॉन के नॉट। थोड़ा सा मैथमेटिक्स है, आई एम श्योर यू कैन ईजिली अंडरस्टैंड। देखिए एक ये इक्वेशन है, एक ये इक्वेशन है और एक ये इक्वेशन है। इफ आई सब्सट्रैक्ट दिस इक्वेशन फ्रॉम दिस इक्वेशन, राइट डाउन ऊपर आई एल के नॉट एफ ई प्लस 3 बल्क और उसमें से सब्सट्रैक्ट कर रहे हैं आई इज इक्वल टू के नॉट एफ ई प्लस 3 बल्क माइनस ब्रैकेट ओपन कर लो तो के 3 फिर के आ जाएगा के नॉट एफ ई प्लस 3 एक्स इज इक्वल टू 0। तो क्या क्या कैंसिल आउट हो जाएगा, के नॉट एफ ई प्लस 3 बल्क ऊपर भी है नीचे भी है, तो इट विल गेट कैंसल्ड आउट। द फाइनल इक्वेशन विल बी आई एल माइनस आई इज इक्वल टू ये टर्म और ये टर्म कैंसिल हो गया, क्या बचा के नॉट एफ ई प्लस 3 एक्स इज इक्वल टू 0 बाई सिंपल मैथमेटिक्स, जस्ट लाइक वी सब्सट्रैक्ट क्वाड्रेटिक इक्वेशंस। तो वही लिखा है आई एल माइनस आई इज इक्वल टू के नॉट एफ ई प्लस 3 एक्स इज इक्वल टू 0 एंड फ्रॉम देयर एफ ई प्लस 3 एक्स इज इक्वल टू 0 विल बी इक्वल टू आई एल माइनस आई अपॉन के नॉट। उसको we have a similar reaction for reduced species as well, मतलब as well अगर हम Fe का रिडक्शन करें, रिवर्स कर दें रिएक्शन को, Fe रिड्यूस हो रहा है, Fe प्लस 2 से Fe प्लस 3 बन रहा है, एक आयंस निकल रहा है Fe प्लस 3 बन रहा है, तो उसके लिए भी यही रिएक्शन होगा। वहाँ पे IO था या KO था बिकॉज ऑफ ऑक्सीडेशन, हेयर वी यूज KR, रिडक्शन हो रहा है, I इज इक्वल टू KR Fe प्लस 2 बल्क माइनस Fe प्लस 2 x इज इक्वल टू 0। क्लियर? अब बट एट द स्टार्ट ऑफ रिडॉक्स रिएक्शन Fe प्लस 2 तो एबसेंट था, बल्क में तो बिल्कुल नहीं था ना, जो भी बना वो इमीडिएटली इलेक्ट्रोड सरफेस पे बना। देन अगेन I इज इक्वल टू KR बिकॉज सिंस देर इज नो Fe प्लस 2 ferrous ions in the bulk of the solution, so this Fe plus 2 bulk will be 0 and I is equal to KR Fe plus 2 x naught. So from here Fe plus 2 x naught will be equal to I upon KR, I upon KR, and K is again NFAD upon delta. Don't confuse, KR is equal to NFAD upon delta. Now substituting the values, because in this equation for calculating the standard state potential, this is known, this is a constant term, N is also 1. What do we need? These are the two concentration terms which we need, Fe plus 2 concentration near the electrode and Fe plus 3 concentration near the electrode. Now Fe plus 3 concentration at electrode we have calculated by this relation using the limiting current, while Fe plus 2 we have calculated with the help of the reverse reaction where oxidation is taking place, this one. Now putting these two value, Fe plus 3 x naught यहाँ रखो and Fe plus 2 x naught put over here, x is equal to, when we put these equation we will get this particular equation, this. Clear? Now if we know the value of current we can calculate, because KO and KR are constant, depends upon NFAD upon delta, N is 1, this is also known, plus 0.356 volts. Putting the values you can easily calculate the standard state potential if you know the value of current. Clear? Now suppose we replace the current with, for example we consider that current is equal to half of the limiting current, I is equal to IL by 2. Just put I just replace I with IL by 2, means the current is half of the limiting current value. The moment you replace I with IL by 2, the equation turns out to be this. And the potential, the standard state potential in such a condition is called as half wave potential. I am sure you have heard the word, those who are working, research scholars, they must have heard the word half wave potential. So, half wave potential is nothing but the potential when the current is half of the limiting current. When the current is half of the limiting current value, the corresponding current is called as half wave potential. That is it. So, it will lie somewhere here, because it is I versus V graph, it is I current versus potential graph, and this is the limiting current value. इसको आप, if you draw the perpendicular from this y axis, you will know the value of current. For example, here it is 1 ampere, so we will take 0.5 ampere, draw perpendicular in this direction, again in this direction. So, this particular point at which this curve is cutting, the intercept is cutting on x axis, this is called as half wave potential. So, what is the criteria for calculating half wave potential? What is the method? If you have the curve, first of all identify the value of limiting current. कैसे निकालोगे? यहाँ से draw straight line, the intercept cut on y axis is the value of current. Suppose it is, for example, 0.8 milliampere. If 0.8 milliampere is the limiting current, take half of its value, 0.4 milliampere, come at 0.4. At 0.4 again draw a straight line to the curve. The point at which this straight line cut the curve, draw another straight line towards the x axis. Now, this straight line, the point at which this straight line cut the intercept at x axis, this, because this is potential axis, now the point at which it is cutting this potential axis is called as the half wave potential. So, in this way, with the help of the curve only, you can first of all identify the type of mass transfer processes occurring, then you can calculate the limiting current, you can calculate the concentration of the species like the analyte Fe plus 3, you can also calculate Fe plus 2 concentration, and then finally you can be able to determine the potential value, which is called as the half wave potential, by just putting the current equal to half of the limiting current. Now, let us take some linear sweep voltammetry. Varis, just a second. The slides are not changing, I think. I want to escape. इसको 1 मिनट करना है escape मुझे. Just a second. इसको करो. हटाओ, escape करना है इसे voltammetry. escape करना है, escape हो गया. शॉर्ट में लिखना है. ठंडा पानी नहीं है, ठंडा देखो करो. शाह सर को कॉल कर बात है ना. थोड़ा सा पानी ठंडा कर दो बस. बाहर अब वो है, अब असफर सर या शेख सर 11:30 चाय हमसे बोल देना. क्या लग गई? How many students are attending online? वो कर दिया, अनम्यूट किया, अनम्यूट किया. I hope you have understood the concept of LSV, voltammetry, amperometry, limiting current, half wave potential during this lecture. Now, let us dive into LSV, the linear sweep voltammetry. Both CV and LSV are influenced by the mode of mass transfer. The nature of the curve will be different depending upon the mass transfers. So let us first see the concentration profile of an species in an unstirred solution. Then we will see for stirred solution. Unstirred solution. First look at this graph, this one. It is in the start of reaction. We only have Fe plus through, Fe plus 3, no Fe plus 2 is there. So suppose we have a system, इलेक्ट्रोड्स हैं दोनों, एक और इलेक्ट्रोड है और हमने Fe plus 3 ऐड किया इसके अंदर. Suppose we have this system, यहाँ हमने Fe plus 3 ऐड किया है. Now no Fe plus 2 is here because the reaction is not started. As the time passes, we have given some potential. For example, in the initial 0.6 seconds, the potential is around 0.495. Nothing will happen. But as the potential start decreasing, because as it comes closer to 0.356, 0.37, 0.38, the reaction will start and will get formation of plus 2 by the reduction of iron plus 3. Since the potential is not of that particular value, nothing will happen. But as the reaction proceeds, just after double this time, from 0.6 second, it is now 1.392 seconds. The potential again drops to 0.46 and it is coming closer to 0.356. There is a small current flowing in the system. Why? Because Fe plus 3 is now getting slowly reducing into Fe plus 2. So this is the first curve where points at 0.69 second nothing is happening. But as the reaction proceeds, this is the second one, as the potential drops down, some little Fe ions are getting Fe plus 3 ion are getting reduced to Fe plus 2, a small current is generated. As the reaction proceeds further, the potential is coming down. You can see earlier it was straight line, nothing happening, but now here a small curve. Again, as the time passes, after 2.088 seconds, the curves are even clearly visible. The current value is increasing. These are the two processes, oxidation one side and reduction. Again, you can see as the potential is coming close to 0.356, it is now 0.391. Again, the current values are increasing. And in this, you can see since it has already crossed 0.356, we have high current values. Then, since we are considering an unstirred solution, which means that only migration is taking place, only convection is taking place. No, sir, only diffusion is taking place, because we are not stirring the solution. We are only considering diffusion as a mass transfer. And I told you that in case of diffusion, when all the Fe plus 3 ion are, because as long as the Fe plus 3 ion are reducing, the current goes up. Now the concentration of Fe plus 3 ion is decreasing now. The current will decrease and a point will come where no current will flow, because again the concentration becomes equal for Fe plus 3 and Fe plus 2. So we'll get a peak current. Similarly here also we get a peak. After 4.176 seconds and at the voltage of 0.3521, the current is still going up. Again it is going to the top. This is the top and again it turns down. So it gives you a shape of a peak. So this shows that we have a peak current, and whenever you got either in LSV or in CV this sort of curve, this shows that you are not stirring the solution and you have diffusion as the mode of mass transfer only. The concentration of Fe plus 3 decreases while the Fe plus 2 concentration increases. The thickness of diffusion layer also increases and we get a peak current. As I told you that since convection is not taking place, only diffusion is there. So the thickness of the diffusion layer keeps on increasing, and from this equation we know that this current is inversely proportional to the thickness. As the thickness of the diffusion layer goes up, the current from its peak value goes down. Therefore, we are getting a peak because as the thickness increases, current decreases. They are inversely proportional to each other. Let us consider the concentration profile in an stirred solution. Again, see that this is the first curve where we have a system, electrode, we have ferric cyanide and a magnetic bar inside which is stirring this solution, or by some other means we are stirring the solution. Since we are stirring the solution, the concentration of Fe plus 3 remains uniform all the time. Even at one end near the electrode, the moment it gets it gets reduced to Fe plus 2, at the same time more Fe plus 3 ions will come, and due to the stirring of the solution, it becomes again uniform. And since this time we are having a uniform current, uniform concentration, the current also increases gradually. There is nothing like a peak current. There is no peak observed in this particular case. Initially, as in this case, we have first of all observed at 0.69 seconds and at the voltage of 0.495. Nothing was there, no current was there. Similarly, here also no current. As the potential decreases, as the reaction proceeds, we have some curves which shows that current is being generated. As the reaction proceeds further, the current goes up, and ultimately it is going up, and finally we have this type of curve. No peak, because all the time the concentration remains same. So I told you, in case of stirring, in case of convection, it is a limiting current. Limiting current means we have a smooth curve, no peaks. So again it is a smooth curve, while in this case we have a peak, we have sharp peak. Here we have quite a smooth curve. So this type of curve, even if it is a portion of a CV curve or a LSV, the curve will be smooth as long as you are stirring the solution. Most of the time we do not stir the solution in CV, so we get peaks. While in LSV we sometimes stir, so the curves are mostly smooth. Clear? Now let us talk of cyclic voltammetry. You all are aware in the previous few lectures on day 1, 2 and 3, especially on day 3, that cyclic voltammetry is a special class of voltammetry in which we scan the potential in both the direction, in forward as well as the reverse direction, and therefore we collect information of the forward process, which may be oxidation, and its reverse process, which is reduction, or maybe a forward process which is a reduction and its reverse process which is an oxidation process, because it is a cyclic process. I told you that in case of cyclic voltammetry, we select the potential window, for example, from 0 to 1, and then from 1 to 0, or from -1 to +1, and then from +1 to -1. So the potential varies in this manner. For example, we have select from negative, for example, -1, it is going to +1 and then back. Similarly, for example, if it is -1, it goes towards the positive side. Then from positive, it again goes to the negative side. So the potential varies in this manner. Draw this curve in your copies. This is the way potential is being monitored, or the potential is being varied in case of cyclic voltammetry. Now we monitor the current correspondingly, and then we plot a graph between current and voltage. The curve for the plot comes like this, called as a duck shaped curve. These are the curves. And from this curve, you can see that if I ask you, you find a peak over there. So in cyclic voltammetry, we vary the potential in two directions, and we study a detailed electrochemical process both in forward as well as the reverse direction. In this particular example which we are considering today, the reduction of Fe plus 3 to Fe plus 2 and then its reverse process. So first, if we give the scan, we scan the potential to a more positive value, for example minus 0.5 to plus 0.5, it shows oxidation of Fe plus 2 and Fe plus 3. So in the forward direction we have Fe plus 2 which is undergoing oxidation to form Fe plus 3. Then when this potential reverted, because if we are doing LSB only, it will provide information about this particular reaction, but not about this reaction. Since we are doing cyclic voltammetry, we will get information about the both the processes, both the reactions, the forward as well as the backward. So when the potential revert back from that predetermined value in the reverse direction, we'll get the reverse reaction, which is the reduction of Fe plus 3 to Fe plus 2. And we collect information and the potential and the peak current for both these reactions. Now the peak current in cyclic voltammetry is calculated by Randall-Savick equation. The peak current IP is given by 2.69 10 raised to the power 5 n to the power 3 by 2 a d 1 by 2 nu 1 by 2 and c. All these are constant except the word, this term C. C is the concentration of that electroactive species, the concentration of analyte for forward reaction. This analyte is Fe plus 2. For backward reaction, this analyte is Fe plus 3. ये रिएक्शन यहाँ से स्टार्ट होती है, ये कर्व बनना यहाँ से स्टार्ट होगा इस टाइप से, ठीक है. Now for forward reaction, you can apply the same equation. For backward reaction also you apply the same equation for forward, but for forward equation the concentration C is Fe for the concentration of Fe plus 2. For the other reaction it is for Fe plus 3. Now n is the number of electrons which are being involved. In this particular it is 1 because Fe plus 3 is undergoing reduction or Fe plus 2 is undergoing oxidation and 1 electron is transferring. D is the diffusion coefficient of the electroactive species. Nu is the scan rate. मैंने बताया था you have to select the scan rate, at what scan rate you are changing the potential, and finally is C is the concentration of electroactive species, A is the area, and from this you can calculate the peak current. Clear? So the CV curve starts from here and then it forms a duck shaped curve. So this is your forward process, this is your reverse process. This is your forward current, peak current, this is your reverse peak current. Clear? This is your forward peak current, this is your reverse peak current. Now when you calculate the peak current for both forward and backward processes, you divide it. And if the ratio of the peak current of the forward as well as the backward reaction is 1, the system is a well behaved electrochemical system. Means the total number of ions which are oxidizing is equal to the total number of ions which are reducing. For example, if 10 ions of Fe plus 3 are undergoing reduction to form Fe plus 2, same number of 10 ions are from Fe plus 2 undergoing oxidation to form Fe plus 3. Same number of ions are involved in the forward and backward processes. The same amount of current will be generated. The ratio of the peak current will be 1, and this shows you that your system is a well behaved system. On the other hand, if this value is not same, if this value is not 1, then that shows that there are some other reactions taking place. For example, if you have iron in plus 3 state, ferricyanide, it is getting reduced to Fe plus 2. Now the moment Fe plus 2 is formed, for example, if there is an impurity in the system which is very prone to attack on Fe plus 2, it will immediately attack, it will immediately react with Fe plus 2 to form a stable compound. Now since Fe plus 2 no longer exists, how will it form Fe plus 3? And if this is the case, the curve will be like this, that you get a peak in the forward reaction but no peak in the reverse reaction, because in the forward reaction you have ions that undergo reduction or that undergo the electrochemical process to give you the other ion, but the moment it is formed, it is immediately reacted with some impurity as a competing reaction. It forms certain other compound. Now it is no longer left. Then who will revert back to via this reaction? So in the backward reaction, no peak will be observed. And in these two curves, you can see that we are getting peaks. That means we are not stirring the solution. Convection is not taking place. For a cyclic voltammetry system, if you want to calculate half wave potential, just add the two peak current and divide by 2. So the half wave potential in a cyclic voltammogram curve is given by EPA, the peak anodic current plus the peak cathodic current divided by 2. So by dividing with 2 and adding these two current, you can easily determine the half wave potential for a CV system. Let us come to amperometry. Amperometry is very useful for sensing. Voltammetry is mainly preferred for energy storage applications. Even voltammetry can be used for sensing as well, but we prefer mostly voltammetry for energy storage and all those type of characterization and for sensors, because amperometry was very first developed for a sensor. It is the technique which measures current as a function of time at a fixed potential. The potential value is fixed. At that fixed value, we calculate current as a function of time. The technique, the amperometric sensor was first developed by, the first amperometric sensor was developed by L.C. Clark in the year 1956. And with that sensor, he measured dissolved oxygen in the blood. Now, what is the sensor all about? That sensor consists of? His sensor basically consists of two electrodes, and there is a membrane which allows only a particular type of gases to pass through it. He uses a gas permeable membrane which allows gases only to pass through it. That gas permeable membrane is stretched across a sensor in which the electrodes, there are two electrodes, then there is a KCl layer, and after KCl layer we have that gas permeable membrane. So at the top of the surface of the sensor we have gas permeable membrane, inner side we have KCl, and then we have electrode. I think I still have some time left. We'll be having tea at 11:30 or 11 o'clock. I think it's 11:30. No, sorry, 11. Because today I started the lecture a bit early. Although it was scheduled on 9:30, I started at 9:45. So I'll continue it till 11:15. So the top layer of that sensor is a gas permeable membrane, then we have KCl layer, and finally we have two electrodes. One side we have this AG ring electrode, this ring is silver electrode, and at the center we have PT disc. Now that gas permeable membrane, when we put a drop of blood, it allows only gases like N2, O2 and CO2 to diffuse through it. N2 when diffuse, nothing will happen. It is not going to oxidize, neither CO2. Even when all three gases diffused inside, only oxygen will get oxidized. So nothing to worry that if N2 is also getting diffused, we should use only that membrane which allows oxygen only. No problem. If N2 and CO2 are there, only oxygen will get uh, reduced. Now when we put a drop of blood, the dissolved gases present passes through the membrane, reaches inside, The moment oxygen gets in, it is reduced, and iron, this oxygen gets reduced at platinum electrode, and iron electrode undergo oxidation. Ag forms Ag plus 2, Ag plus 1, and that electron is taken up by oxygen for reduction. In this way, electrons are moving, a current is generated, and this current is proportional to the concentration of oxygen. Higher the concentration of oxygen in the blood, higher will be the current, or vice versa. If you are getting higher current output, that means the blood, the dissolved oxygen concentration is high in the blood. So this was the first sensor, which is an amperometric sensor developed by Dr. L.C. Clark. Similarly, we have a blood glucose sensor, which we all are using, we all are aware of. A blood glucose sensor has an electrode where we put a drop of blood. Now, we replace the glass membrane, which is used in blood oxygen sensor, with three different membranes in case of blood glucose sensor. The first, the outermost membrane provides strength also. It provides as a, it is a protection also for the rest of the layers. This layer is made of polycarbonate, very strong. This polycarbonate layer is permeable to glucose and oxygen only. So when you put a drop of blood, first of all, this polycarbonate keeps the other layers protected, and when you put the drop of blood, only glucose and oxygen diffuse in through this layer. When it enters, because there are three layers, after this polycarbonate layer, we have a layer of an enzyme, glucose oxidase, which can oxidize glucose. The moment glucose and oxygen reaches there, the glucose is oxidized by glucose oxidase immobilized enzyme, immobilize कर देते हैं, layer बना देते हैं, to form gluconolactone. Electrons are released. On the other hand, the third layer is cellulose acetate. Immediately the oxygen is reduced and it forms H2O2. The polycarbonate membrane allows glucose and oxygen to pass through it, where glucose is oxidized to gluconolactone and H2O2. Now H2O2 is oxidized to oxygen, and in this way, H2O2 is oxidized to oxygen, and in this way, a current is generated. And since the electrons are being released from glucose during the formation of gluconolactone, these electrons are proportional to glucose concentration. So the current is proportional to glucose concentration. If the amount of glucose in blood is high, the current will be high. So this is also an electrochemical sensor, or electrochemical sensors gives you either value in the form of current or the voltage, and this current and voltage is directly proportional to the amount of or the concentration of analyte. And in this way, based on the value of the current generated, there is already a calibration curve drawn and fitted well into the transducer. The transducer is the machine that converts that data into useful information. So on the basis of that calibration curve, from the current value, it calibrates backward to give you the concentration, to give you the amount of blood, to give you the amount of glucose in your blood. Now, what points one should consider while selecting an appropriate voltammetric technique? Amperometry, we have this technique only. In voltammetry, there are several techniques. These are the techniques which I have shown during the classification. These are different techniques: hydrodynamic, stripping voltammetry, then we have LSV, we have pulsed potential voltammetry, then we have CV. So which technique we should use for our analysis? So there are certain points which must be considered. The choice of voltammetry depends upon the nature as well as the concentration of sample and its location. For example, you are doing analysis of something in a flow system. For example, you are analyzing some component in blood. So it is a type of flow system. We always prefer amperometry for that. because amperometric sensors are portable, they are more reliable, and they can be used for real time analysis. Now if you have to use voltammetry techniques, then we have to first of all know the possible detect the concentration limits of the component. For example, if we are using polarography, the limit of detection of polarography, if we compare it with stripping voltammetry, is less. Stripping voltammetry means we are using a voltammetric technique in which we are stirring the solution, in which we are allowing convection to occur as a mode of mass transfer along with diffusion. The stripping voltammetry may we allow the convection to occur along with diffusion. So if we compare, the limit of detection of stripping voltammetry is much higher. Means if we can detect even very low concentration, 10 to the power minus 12 molar. So if some analyte is present at very low concentration, for example 10 to the power minus 11 molar, and if you detect it with polarography, you won't get any answer. It shows that the analyte is absent. But if you use the stripping voltammetry, it will give you a reliable information about the concentration of that analyte. So we have to select a particular technique depending upon the nature of sample, the nature of media in which we are. For example, it may be flowing water, it may be blood, or whatever it is, and also on the limit of detection as well as sensitivity of the technique. Thank you very much for patience listening. I think I have taken 10 or 15 minutes extra. If you have any question, I would be happy to answer. Anyone from the online participants also? Fuel cell, I can explain, but it will again take more time. One more lecture is needed for fuel cell. But in fuel cells also, we characterize a fuel cell as well with the help of cyclic voltammetry, because in fuel cell also, fuel cells are basically energy generation devices. Or you can say energy converting device. They convert, for example, a fuel cell either convert a chemical energy into electrical energy, while batteries and capacitors are energy storage devices. So both involves energy either in the form of storage or in the form of conversion. So we characterize a fuel cell also with the help of CV and LSV. Let's move for a cup of tea and then we'll back again in this room. Thank you, sir. Thank you.